Uh, Good.
Hello teacher, my name is Lâm Thế Văn. I'm from Faculty of Mechanical Engineering and today I'm gonna represent about the topic function. Function find practical application in real-life math problems, enabling us to modelize and analyze diverse scenarios. For instance, in finance, compound interest formulas utilize exponential function to calculate investment growth over time. In architecture, structural analysis employs functions to determine load distribution and stress pattern in buildings. Epidemiology relies on functions to predict the spread of diseases. Functions also guide animation in computer graphics, predict consumer behavior in marketing, and describe natural processes such as radioactive decay. From predicting stock prices to designing stable structures, functions are the mathematical backbone that empower us to coherent and manipulate the world around us. So let's go into detail of some math problems. In example 1, we will explore the radioactive decay calculation. Suppose we're studying the decay of radioactive substance. The substance have a half-life of 10 years, and you interested in calculating how much of substance in remain after 30 years. So we have the formula of radioactive decays of a substance, typically modeled by using this, where Nt is remaining quantity of substance after time t, and N0 is the initial quantity of substance, T is the half-life of substance, and T little t is the time. And we plug the given values in the statement. So N0 is not given, but we can consider it to be 1 or 100%. And T half-life is 10 years, as you can see. And T time is 30 years. So now we have the formula Nt will equal to 1 times 1 and 1 over 2 power 30 over 10, and that will total equal 1 over 8. So we have this conclusion after 30 years, approximately 1 over 8 or 12.5% of radioactive substance will remain. This is a result of the substance undergoing radioactive decay over time, with its quantity halving every 10 years. Radioactive decay is an essential concept in environmental science, as it helps us to understand the behavior of radioactive materials and their potential impact on the environment and human health. Let's take another look at the second example, the maximum revenue in business. Suppose you are managing a business that sells a product, and the revenue generated by products can be represented by a function Rx, where x is the number of units. So the revenue function is given by Rx equal to 20 times x minus 0.5 times x power to 2, where Rx is the revenue of in dollar and x is the number of units sold. So you want to find a maximum revenue that can be obtained from selling this product. We need to determine the value x that maximize the revenue function Rx. So this involves in finding the critical points of function by taking its derivative and setting it equal to 0. So first we must find the derivative of Rx with respect to x. So we have this rule of differentiation dr over dx, and so we have the derivative of function Rx is equal to 20 minus x. So step 2, we set the derivative equal to 0 and we find that x equal to 0. So evaluate the second derivative at x equal 20 to determine the nature of critical point. So we have d power 2 r and over d x power 2 will be equal to minus 1. So since the second derivative is negative, this confirms that the critical point x equal to 20 is maximum. So the maximum revenue is obtained when x equals 20 units are sold. Plug this value back into the revenue function to find the maximum revenue. So we have R20 will equal to 20 times 20 minus 0.5 times 20 power to 2. That will be equal to $200. So that's all of my presentation. Thank you for listening.
Hello you guys, my name is Bùi Nguyễn Minh Thư. I'm a sophomore at Ho Chi Minh University of Technology. Today my presentation is about application of derivative in position, velocity and acceleration. First, from our study of calculus so far, we know that the average rate of change in the slope of the secant line between 2 points on the graph, the instantaneous rate of change is the slope of the tangent line at a single point. Let us connect these points to position, velocity, and acceleration. First, I'm going to talk about position and velocity. From our study of physics, we know that to find the average velocity of a particle, you divide the total displacement by the total time. Following the formula, the average velocity equal to the final x minus the initial x divide t final minus t initial. Essentially, if we look at a position time graph, the average velocity is the slope of the secant line between 2 points. To obtain the instantaneous velocity at a particular time, we need the slope of the tangent line at the particular point of the position time graph. In other words, we need to take the derivative of the position function bt to obtain the velocity function. Subsequently, about velocity and acceleration, from our study of physics, you know that to obtain the average acceleration, you divide the change in velocity by total time, with average a equal to final v minus initial v divide final t minus initial T. So here are some examples. We are given the position function bt and we need to find the acceleration at any time t. And here we have following formulas which is used commonly in physics. We have b comma t equal to vt equal to t minus 1 and b double comma t equal to at equal to. So therefore we have the acceleration at any time t is 2 just according to the formula. We apply the previous formula to example 2 and 3. To conclude, not only derivatives applied in velocity and acceleration, but also in many aspects of life.
Hello teachers, hello everyone. My full name is Khanh. I'm studying construction engineering and I'm also junior student. So we go to my problem, minimizing cost of packaging. So why I choose this problem? In our daily life, we often encounter scenario where we need to make efficient and cost-effective decisions. One such scenario involves designing packages for a cylindrical product. Imagine you are part of a team responsible for designing packaging solutions that not only protect the product but also minimize the manufacturing costs. This seemingly simple task can have a significant impact on the company profitable and environmental sustainability. Why this problem is important in our real life. The problem of minimizing the cost of packages is not just an exercise in mathematics. It directly relates to real-world considerations. By optimizing packaging design. Companies can achieve multiple benefits. First of all, cost savings. Minimizing the use of material can lead to substantial cost saving over time. In a competitive market, even a small reduction in manufacturing costs can result in higher profit margin. Secondly, efficient packaging design can contribute to reduced waste and using fewer resources. It aligns with modern trends towards sustainability and environmentally friendly practice. The next one is resources allocation. Designing packages that utilize resources efficiently help make the most of available material and reduce unnecessary waste. Moreover, logistics and transportation, smaller and lighter packages can lead to reduced transportation costs. A small product can be transported in a single shipment. And the last one is consumer appeals. Well-designed packaging can enhance the product visual appeals and influence consumer perceptions. So we go to the detail of my problem to illustrate the process. Let's consider a specific problem, minimizing cost of the packaging for a cylindrical can while keep its volume constant. Here how the problem can be solved step by step. First of all, defining variable and constraint. We have radius here, we have height here, and we are given that volume V of cylindrical cans is about 500 cubic centimeters. So we have the equation here. We calculate the cost of manufacturing by the sum of the cost cylindrical body and the cost of circular top and bottom. And we calculate the cost of cylindrical bodies is proportional to its lateral surface areas, and the cost of circular top and bottom is proportional to their combined areas. So if we want to minimize the cost of C's while keeping the volume is constant, we have the equation here. Now we can express x in terms of using the volume equation. After that, to minimize the cost, we need to find the critical point of conversion by taking its derivative with respect to r. And we calculate this here, and we set derivative equal to 0, and so for r. So we have the results here. Since r represent the radius, we discuss the negative roots. So the critical radius that minimizes the cost is approximately 8.92 centimeters. And the last one, we calculate the corresponding height using the volume equation. And we have here. And I have conclusion here. You can read it. Um, in so about my thinking conclusions. The problem of minimizing the cost of packaging highlight the practical application of calculus in optimizing reward decisions. By using mathematical technique to optimize packaging design, company can enhance their competitiveness, reduce waste, and contribute to sustainable practice, while consumers benefit from more appealing product and potentially reduce costs. Thank you for listening.
Hi everyone, today I will introduce about two topics I will choose for our project. First, I will choose something that deals of my major because my major is food technology, so that I will choose the topic about chemistry. In the hydrogen atom, you have several series of spectral lines. For example, the Beimer series in the series of electron transition from a bond level n equal to 2 down to n to level n equal to 2. The Beimer spectral lines are the only lines of hydrogen that are in the visible range. Each spectral line series has what is called the series limit, which is the wavelength or frequency radius during a transition from n equal to infinity down to where the electron finally ends up, n equal to 2 in the case of the Beimer series. The series limit represents the shortest wavelength or highest frequency at which the atom radius in the particular series. In the case of hydrogen, we can use the Rayleigh formula to calculate the wavelength or frequency. The Rayleigh formula is 1 divided wavelength R1 divided N1 square minus 1 divided N2 square, so that N1 is the lower energy level and N2 is the upper energy level. N2 is bigger than N1 and R is the Rayleigh constant. For a spectral series where the electron lands at level N1, the series limit is obtained from 1 divided wavelength is equal to limit n to infinity r1 divided n1 square minus 1 divided n2 square and equal to r divided n1 square. So here you have an example in chemistry where the concept of limit is applied. And the second topic, suppose an object is acted upon by a constant force F5, Vt, and St by Newton's law F equal to ma, so the acceleration is F divided m, where m is the mass of the object. Then we first have some math using the usual convention V0 equal to Vt0. Then we have some math equal to S0 plus V0 t minus T0 plus f divided 2mt minus t0 square. For instance, where f divided m equal to minus g is the constant of gravitational acceleration, then this is the following body formula if we neglect air resistance formula from elementary physics, or in the common case that t0 equals
Phan and I'm currently in my third year at University, and my major is mechatronics engineering, and my interests are reading books, playing games, and talking to people. I'm usually praised for my creativity and teamwork skills. People also describe me as a careful and dependable person, and that's some information about me. So about today's topic, we have to apply calculus 1 to solve real problem. So I'm gonna choose the topic cooling a hot object. So first of all, imagine you are present with a situation where a hot object needs to be cooled down. This could be a cup of tea that's too hot to drink, or an electronic device that's been running at a high temperature, and you want to understand how the temperature of the object change over time as it cools down in a room at a lower temperature. And this cooling process can be quantified using a mathematical function. And this problem engages the principles of limits and continuity in calculus to model and analyzing the cooling process. So, um, so here we can see that this function tt is equal to 100 multiplied by e raised to minus 0.05 t plus 20, where t is the timer in minutes and tt is the temperature in degrees Celsius. So first of all, in order to find the temperature at the specific time, let's explore the scenario where you are curious about the temperature of the object after a certain period. Say, I would say 30 minutes, and you can find the temperature by plugging t equal to 30 into the temperature function we got over here, and you're gonna got this result, and it is approximately equal to 42.31 degrees Celsius. So this implies that after cooling a period of 30 minutes, the object's temperature will be approximately 42.31 degrees Celsius. This insight is particularly useful when you want to ensure the object is at a safe or comfortable temperature before handling it. go to the next part, which is analyzing the limit. The concept of limit is foundation is calculus and is especially pertinent here. By examining the temperature function Tt as T approaches infinity, you have essentially studying the behavior of cooling process in long term, and the limit of T approaches infinity is calculated at this over here. Lim T approaches infinity of Tt equal to lim equal to this, and we calculate that it is equal to 20. And this result indicates that as time stretches on indefinitely, the object temperature will eventually stabilize at 20 degrees Celsius. This aligns with the room temperature, and it signifies that the cooling process will eventually reach the equilibrium where the object is as cool as its surrounding. Go to the third part, which is how to ensure the continuity. So continuity guarantees that the smoothness of a function graph, implying that there are no sudden jumps or breaks. In the context of this problem, the function Tt is continuous across all points. This ensures that cooling process unfolds gradually without any abrupt temperature changes. The function smoothly transitions as the object cools, making the mathematical model a reliable representation of a physical process. And in the last part, we learn on how to find time on a specific temperature. So let's say you are interested in determining how long it takes for the objects to cool down to a desired temperature, such as 30 degrees Celsius. And to address this, you set up an equation using temperature function, which is here. The Tt is gonna be equal to 30, and you're gonna solve. After solving this, you will get the result that T is approximately equal to 46.05. So this calculation unveils that it will take around 46.05 for object to cool down to 30 degrees Celsius. And in conclusion, this comprehensive problem demonstrates the practical application of calculus concepts, limits, and continuity in comprehending the cooling process of a hot object over time. By utilizing these mathematical principles, you gain insights into the cooling trend, ensure the smooth transition of temperature, and calculate the time required for the object to cool a specific temperature. This real-world scenario exemplifies the versatile utility of calculus in understanding the natural phenomena. So that's all of my problem. Thanks for listening.
My name is Phúc Toàn. I'm from student of Ho Chi Minh City University of Technology. I'm from the Computer Science and Engineering faculty. Today I'm going to talk about my project of Calculus 1. My project is about forecasting the population of Vietnam using integral. As my research, I got to know that around 100,000 people moved to another countries like the United States, Japan, or Australia each year, while there are about 80,000 people choose to move and live in Vietnam. And last one, I'm going to talk about the importance of population forecasting, like resource allocations. Accurate population forecasts help the government to allocate resources more effectively. Economic and policy planning help the government to make informed economic decisions and inform the creations of policy related to various sectors like housing, employment, social services, and environmental sustainability. Healthcare and social services are crucial for healthcare planning. Hospital, clinic, and other healthcare facilities need to be prepared to handle healthcare needs of growing populations. And there are so many things that need the population forecasting to be worked on, like urban development, education planning, and disaster preparedness. And this is the end of my project. Thank you.